Hello, I'm Professor von Schmohawk, and welcome to YU. In the previous lecture, we introduced logarithms and saw how logarithm tables were initially developed as a way to simplify and speed up calculations involving multiplication and division. We also introduced the logarithmic function and saw that to evaluate a logarithm with a base b, we ask what exponent would the base need to have to be equal to the function's input variable x. For example, if the base of the logarithm is 10 and x has a value of 100, since 10 squared is 100, the log base 10 of 100 is 2. In this lecture, we will see how logarithms are typically used today. We saw in the previous chapter that the logarithmic function and the exponential function are closely related inverse functions. The difference between an exponential function and a logarithmic function is which two quantities are given and which quantity must be determined. In an exponential function, the base and exponent are given quantities, and the resulting value must be calculated. On the other hand, in a logarithmic function, the base and resulting value are given quantities, and the exponent that produced that value must be determined. As we have seen, exponential functions are used in calculations involving systems that grow or decay, where the rate of change of the function is proportional to its current value. One example of this is the growth of continuous compound interest that we saw in Chapter 96, Exponential Functions and Compounded Interest. At every point on the graph slope is proportional to its current value, which is a characteristic common to all exponential functions. We have seen that the base of an exponential function can be any positive real number other than 1. Likewise, the base of a logarithmic function can also be any positive real number other than 1. However, the base values most commonly used for logarithms are 10, 2, and the irrational constant e, which is approximately equal to 2.718. Since a logarithm's base can be any positive real number other than 1, why are these three base values the most commonly used bases for logarithms? So let's examine these three logarithms a little closer to see why they are especially useful. Since our number system is a base 10 number system, logarithms with a base of 10 are typically called common logarithms and are often simply written as log of x without any subscript. Base 10 logarithms are often used in scientific calculations. For example, in chemistry, a solution's pH level, which is a measure of its acidity, uses a base 10 logarithmic scale. Base 10 logarithmic scales are also used in acoustics to express the intensity of sound in decibels, and in geology to measure earthquake magnitude using the Richter scale. Logarithms with the base value of e are called natural logarithms and are typically written as ln of x without the subscript e. Natural logarithms are used in calculations involving processes that grow or decay exponentially, such as population growth and radioactive decay. Natural logarithms also appear in many other fields. For example, as we saw in the previous lecture, natural logarithms are used in financial transactions to calculate continuous compound interest. Base 2 logarithms, referred to as binary logarithms, often appear in computer science. Binary logarithms are used to determine the number of ones and zeros needed to represent a number and to analyze computer algorithms such as binary search, where the search time required is proportional to the binary logarithm of the input size. Logarithms are often used to scale graphs that contain a wide range of values. One example of this is the growth of bacteria. So let's see how logarithms can be used in charting this growth. Bacteria increase their population by repeatedly dividing. For example, let's say that each bacterium divides once every hour. So starting with a single bacterium, after 1 hour, the single bacterium will have divided into 2 bacteria. After 2 hours, the 2 bacteria will have divided into 4 bacteria. After 3 hours, we would have 8 bacteria, and so on. So after 24 hours, the bacteria's exponential growth will have produced almost 17 million bacteria. Now, if we graph the bacteria's growth, although this graph accurately depicts the population of bacteria during the 24-hour period, during the first 16 hours, the population is too small for the growth to be seen. However, if we display this same information using a semilog graph, making the vertical scale logarithmic instead of linear, now each horizontal line represents a value 4 times larger than the line below it. So starting with a single bacterium, after 1 hour, the single bacterium will have divided into 2 bacteria. After 2 hours, the 2 bacteria will have divided into 4 bacteria. After 3 hours, the 4 bacteria will have divided into 8 bacteria. After 4 hours, the 8 bacteria have divided into 16 bacteria, and so on. In addition to using logarithmic scales for graphs that contain a wide range of values, logarithmic scales can also be used in graphs to produce more intuitive results. For example, if we graph the frequencies of musical notes using a linear scale, where the vertical axis shows the note frequencies, and the graph's horizontal axis shows the names of the notes, the distance between adjacent notes varies throughout the graph. However, if we use a logarithmic scale for the frequency, the graph becomes a straight line with the notes equally spaced, like the notes on a musical keyboard. This type of graph is called a semilog graph, since the vertical scale is logarithmic and the horizontal scale is linear. You may hear it said that logs are exponents. This is true because a logarithm's value is the exponent that its base would have to equal the value of its input variable. So the value of a logarithm is actually the value of an exponent. And because logarithms are exponents, mathematical operations involving logarithms follow the same rules as exponents. For example, a rule of exponents says that if we multiply two copies of the same number, where each copy has an exponent, we get the same value if instead we just add the exponents. Likewise, if we take the log of the product of two numbers, which we will call x1 and x2, the result will be the same as just adding the logs of each number. So let's test this rule. We will assume a base of 10 for the logarithms and give x1 a value of 100 and x2 a value of 1000. 100 times 1000 is 100,000, and the base 10 log of 100,000 is 5. Likewise, the logs of 100 and 1000 are 2 and 3. And since 2 plus 3 is 5, we can see that this rule of logarithms works since taking the log of x1 times x2 produces the same result as adding the logs of x1 and x2. A similar rule states that the log of two numbers x1 divided by x2 is equal to the log of x1 minus the log of x2. To test this rule, we will give x1 a value of 1000 and x2 a value of 100. 1000 divided by 100 is 10, and the log of 10 is 1. Likewise, the logs of 1000 and 100 are 3 and 2. Since 3 minus 2 is 1, we can see that this rule of logarithms also works. Another rule that follows the same rules as exponents says that the log of one number a with an exponent b is equal to b times the log of a. To test this rule, we will give a the value of 100 and b a value of 2. 100 squared is 10,000, and the log of 10,000 is 4. Likewise, the log of 100 is 2, and since 2 times 2 is 4, this rule also works. A related rule says that the log of the b root of a is equal to 1 over b times the log of a. To test this rule, we will give a value of 10,000 and b a value of 2. The square root of 10,000 is 100. The base 10 log of 10,000 is 4. And 1/2 of 4 is 2. Since the base 10 log of 100 is also 2, this rule also works. In some cases, we may know the log of a number, but we would like to know the log of that number with a different base. For example, let's say we know the base 10 log of some number, and we would like to find the base e log of that number. In the next lecture, we will introduce the change of base formula and see how to use this formula to convert the base of any logarithm to a different base.